Hey, what's up, guys? This is Sheng here. So today, let's take a look. LeetCode problem 1687, delivering boxes from storage to ports. So I mean, this is a really difficult problem. Okay, so let's take a look at the problem description. So you have the task of delivering some boxes from storage to their ports, and you only have one ship, and the ship has a limit of the number of boxes that can carry and also the total weight as well. And then you're given like an array of boxes, right? Where the each box has two properties, right? So the first property is the ports the box will go to, and second one is the weight of the box, right? And then you're given like three integers. So the first one is the ports count, the total ports count. I'm not sure if this is really useful or not, but we'll see. And second one is the max of basically the limit of the boxes the ship can take. And the last one is the maximum weight. All right. And then here's how the ship will deliver those boxes. So each of the boxes, let's say we have like bunch of boxes, right? And each boxes has to be delivered in order. So which means that let's say if the first one is going to port 1 and the second one going to the port 2 and 3, 2 and 1, right? So let's see, I'm ignoring the weight for now. If the number represents the port the box needs to go to. So even though we are like, let's say we're assuming we are loading all 5 boxes into the ship, and then the first time the port will, of course, it will go to the port 1, right? And then because it needs to deliver port 1 first before delivering the port it needs to deliver the box 1 first before delivering the box 2 here. That's why the ship will need to go to port 1 first and then unload this box 1, and then it will go from port 1, it needs to go to port 2, and then it will unload this box 2, and then it will go to port 3, right, to unload box 3, and then it has to go back to port 2 to unload box 2, to unload this box, because even though there are like 2 boxes, there are 2 boxes that belong needs to go to port 2, but since they need to be unloaded in the same order, that's why it has to go to port 3 and then come back to port 2, and then in the end it will come back to go back to port 1 to deliver the last box. And this is how the ship will deliver the boxes, right? And each time when the ship from from port 1 to port 2 ships between different ports, it will um, do a one trip. And also from the storage to the first trip, from the storage to the first port, and from the last port back to the storage, right? Basically, the ship will from storage, it will at the beginning it will go to the port 1, and in the end, whichever the port is ended, it will come back to storage. That's why in this kind of trip here, we have 1, 2, 3, 4, 5, and 6. So we have in total 6 of trips we need to make, right? And then the question is asking you to find the minimum of number of trips the ships needs to make to deliver all the boxes to their respective ports. And that's the description. It's a pretty long description, and you have a lot of parameters. And here's are just some examples, right? And I'm not going to go through all the examples, but and then in the end, here are the constraints. Basically, the constraint is like 10 to the power of 5, so which means we can either use O(n) or n log n solution, right? And this is what's making this problem a hard one. All right, so so to get the minimum number of trips, right? We have a bunch of options. I mean, we should try to think about what kind of like solutions we can try, right? I mean, the first one is what is the, the BFS, right? So, but I don't think we have a BFS solution here because there's no clear starting and ending state here. And then we have like what? The next one is of course the DP, right? We can always do the DP. And this problem is actually a DP problem with a little bit optimization on top of that. So why is that? Because the DP, right? So a very naive DP like definition is for DPI, right? So DPI means that to deliver the first ice box, what's gonna be the minimum trips, right? The minimum trips we need to make. And the definition is actually correct, but a naive implementation for this one is let's say we have like this kind of boxes, right? So let's say we are at like this DPI here, right? That's going to be the RI here. So what's going to happen is that, from here go back, right? Since we're going to get some state transition, right? From DP like and DPI equals to some DPK. Let's say DPK plus the trips, right? So this is going to be our state transition, right? From we pick the K location and then plus the trips, right? Between the K to I. So let's say we have a K here, right? So basically, so this one it means that we're going to deliver the boxes from K to I within one trip, okay? And then whatever before K will be the remaining, and the trips delivered from K to I will be the cost, the trips where we need to make, right? And then so the trips will basically will of course depending on how many distinct ports we have in this range here, right? And then that's gonna be the trips. Of course, we have to also consider the storage, the storage, right? So storage, sorry, to coming back to the storage and go and to pick the boxes, and then we go back to the first port. That will be another two trips, right? But that's gonna be the minor thing we need to worry about here. And we'll basically will try. Of course, we have to make sure this from K to I, it's within the limits. It complies with the constraints. First one is the max boxes. It's not exceeding the total number of boxes, and the second one is total number of weight. Right? That's going to be the two constraints we need to follow. And then and after following those kind of two constraints, basically we try each of the K locations from 0 to I, assuming we can pick any of them, right? Assuming we can pick any of the boxes from 0 to I. And that, of course, obviously is a O n square time complexity, right? Assuming we can calculate the trips within O1 time, but still, it's going to be a O n square. And with the O n square time complexity, and with this kind of 10 to the power of 5 constraints, it will most likely TLE. So and that's the difficulty for this problem, and we have to somehow and improve it. And the way actually it improves is we're using like a greedy approach, right? Plus a sliding window approach. Basically, it's the sliding window. It just helps us to calculate the trips more efficiently, and then help us to find the best K we need for the current I. That's our greedy approach. So to remove the nested loop for finding the k here, like I said, we use a greedy approach to find the best k for the current I. And how can we find it? So a general approach to do a greedy is, I mean, it's kind of makes sense, right? I mean, we want to load as many boxes as possible within one trip. I'm sorry, not within one trip, but within the one, yeah, trip from the storage. That's gonna be our uh, general greedy idea here, but we have to tweak it a little bit because, and we don't want to like, let's say for example we have like some ports here. Let's say we have one, two, uh, two, right? And then we have three, one, and one. So let's say we have this kind of ports, right? Assuming we can pick any of those boxes, right? Within the uh, let's say this max boxes is pretty big, right? And we can pick any boxes as we want. So let's say we are at like this I here, right? And then let's say the total, the max weight we have here is that, let's say each of them, the weight is like, is one, okay? Let's say that the max weight we can pick is four, right? So which means that, if we're using our initial greedy approach, it means that we want to pick as many boxes as possible, right? So that from the current I here, we see that, okay, we can pick four boxes. That's why okay, now the k is here, right? And then, but are we going to try to pick from 2, 3, 1, 1? Probably not. Why is that? Because, you guys can see here, if you pick 2 here, we have the next one is 3, and then we have 1 and 1. It means that we have to make two moves, two trips to deliver all boxes because we have three different boxes. But if we leave the 2 to the previously delivery, which means that let's move k one way closer to this place. Let's say we move the k from there to there to here. Assuming this 2 can be delivered within the previous delivery. Now the trips we need to deliver all three boxes will become to 1. So that's gonna be our a little bit of improvements of our naive greedy approach. So which means that, so the greedy approach is, of course, is this. So we try to deliver as many boxes as possible, but with one exception, which is if the current one can be delivered uh, can be delivered with the previous one, and we're not adding we're also not adding we're not also not making the previous one needs more trips, then we will like move the cursor to the right. So how do we check that? Remember, we have a DPI in here, right? So if the DP, let's say if the DPK, that's a DPK. If DPK is equal to the DP K plus 1. So if the DPK equals to DPK plus 1, then what does it mean? It means that it means that to deliver 1 to 2, 3. Well, actually, yeah. So I'm assuming, okay. So to deliver 1 to 2 and also to deliver 1 to 2, 3, they're having they will they requires the same trips, right? So which means that that's actually yeah, actually this is not a good example here. Maybe the two is not, it should be here. I think the k should be here. This is a better example here. So let's say the k is here, and if the dp, right, if the dpk equals to dpk plus k plus 1, and it means that actually the next one has to be the same as the previous one. Otherwise, otherwise if we are not, if these two are different, the dp k plus 1, it will has to be a has to be a has to be one more than dpk. Why is that? Because if this one is different, if this one's different, I mean, to deliver from this port to this port, it will make one more trip. But we're using this one to check if we can move the cursor forward to here, because if the dp is the same, it means that the k the from to deliver from 1 to deliver from 0 to k and to deliver from 0 to k plus 1 requires the same trip, right? And of course that means that we should, since we're using a greedy approach, that means that we should leave the k plus 1 to the previous um, deliver, and that's why we have to move the cursor to here, which means that in this case our best approach is to deliver 311 instead of 2311. Okay, and so that's gonna be our basic approach, to do the greedy plus DP, and I'll just try to start coding here. So the first thing, we have a length of boxes and the DP, right? So DP, we have a system dot max size, right? And then n plus 1. So at the beginning, right, we have DP 0 equals to 0, right? And then we have a weight is 0. We have weight equals to 0, and then we have trips equals to 2. So because the 2 means that we have to for each of the trips we have to come back to the storage to pick some boxes and then go back to the first port. It's going to be additional 2 trips here. So the way we're doing this kind of like greedy approach is that we're going to use a like sliding window approach. So we're going to have a left and equals to 0, and then we have like a for right, right? So this is the way we're doing the sliding window. It means that we are with the current right here, and from the current right, it means that we are trying to deliver from the current right here. We're trying to deliver the right one. We're trying to include the right this box and with some other boxes before us, and we're going to make that one delivery. So with the current right cursors, we're going to increase the boxes, right? With the right cursor and then 1, right? Because the boxes has 2 parameters and we're using the weight here. And so with the current one, and we're trying to see if the current and what's going to be what's going to be the trips for this. So the way we're calculating the trips efficiently is if the boxes, right, if the current boxes is different than the previous one, okay, and it means that we need to make one more trip to deliver the current box from the previous port. right? So that's why we have a box -1, then 0, because we're comparing the port, right? Then we're doing like chips class 1. But since we're starting from 0, right, and we cannot go back to 0 -1, that's why we have to do a check. If the write is greater than 0, right, then and then we can do a write -1. So that's that, right? I mean, if the current box is different than previous one, right? Need to make one more trip. And now what? The next one is the sliding window one, right? We have to maintain the sliding window, right? So basically the first one is this, right? So if the sliding window, the length is not great, it's not exceeding the max of boxes, that's gonna be our first limits here. And the second one is the weight. It's not this current weight, right? So in this case, we're gonna do a what? We're gonna shrink the sliding window, right? So here I'm implementing the very basic greedy approach, which means that we're trying to take mm, as many boxes as possible, right? So now the weight will be what? The weight will be boxes uh, left 1, right? So that's gonna how we decrease the weight, and we're also gonna try to decrease the trips. So the trip is like this, right? So if the box is similar as how we increase the trips, right? If the box is of left and 0, it's not equal to the boxes of the left plus 1 0. So why is that? Because we're trying to take out the boxes from the current sliding window, right? Because we have this is our sliding window, and this is the boxes we're trying to deliver, right? And that's why we have to do a left plus 1 check, because we're comparing the current one we're trying to remove from the ones still in the sliding window, right? So if they are different, then we can decrease the trips by 1, right? So and then in the end, after we have sliding window here, the way we're updating our DP is like this. So with the current one, we are delivering the current one, so which means that since the definition for our DP is and to deliver everything that's starting from uh, let's see. And actually, since we're using like the 0 base here, because it's easier for us to find the boxes, not the 1 base in for the DP. Oh, sorry, I think I forgot a equal sign here. Usually we do a DP, right? We do a DP from 1 to uh 1 to n plus 1, right? And then we can simply use the DPI here. But since here we're using like the left and right pointer just to make it easier for us to loop through this one, or we can do this, or we can we can make this one like a DP here, but when we find the boxes, we have to do a right boxes, we have to do a right -1. That'll be a little confusing. That's why we're using like a left and right with 0 base. But then since the DP is 1 base, right? So we have to do what? We have to do a right plus 1, right? And then equals, oops, equals to a DP left, right? So we're saying that, so this left is our basic, is our best approach to pick, and then we have a trips. So and in the end, we return the DP -1, right? So which means that we to deliver all the boxes, how many trips we need. But like I said, this is just like a naive greedy approach, right? And we have to make a little bit modification. Like I said, we have to check. We need to keep moving the left forward, or left is smaller than right, and the dp left is equal to the dp of left plus 1. So this one means that, if the current, if the left, if the left one, the current cursor one can be or it's be like, or the left plus one can be or the next one can be included within the previous one, previous delivery. We have to move. We have to make sure that one is included into the previous delivery. That's why we also need to move this left cursor forward if this DP is the same. Otherwise, if we don't do this, our current trips might be bigger than we anticipated. And that's the whole implementation. If I run the code, I think, there's like the colon here, accepted boxes. Okay, few typo here. Yeah, and so the time complexity, I mean, it's O of n, right? Because the left always moving forward, even though we have a while loop here, and each element will only be visited twice. That's why the time complexity for this is O of n. Yeah, I mean, just for a quick recap, right? So the basic idea for this problem is a DP, where the DPI means that, to deliver the first ice boxes, what are the minimum trips we need? But since we have a pretty big constraint, we cannot use the naive O of n squared DP solutions, and we have to find a better approach. And the way we are doing it is we are like doing like a greedy approach. So which means that from the current position, which is right, we're trying to load as many boxes as possible while maintaining some conditions, which means that we are not going to include anything that can belong to the previously delivery. And so here's how we maintain the boxes, the sliding window, and then this is how we maintain make sure we can give as many boxes as possible to the previous delivery, because the DP left is equal to the DP left plus 1. It means that by giving this one box to the previous delivery, it will not increase our final, it will not hurt our DP value. Instead, it will help us to reduce the trips by maintaining the first part. So actually, it's kind of a too greedy concept here. Yeah, and that's how we solve this problem. And it is pretty hard. So, okay, let me know what you guys think. And thank you so much for watching this video. And stay tuned. See you guys soon. Bye bye.